In this video, we will be covering the AP Physics 1 Kinematics review. In this unit, we focused on how objects move and how we can describe the motion of those objects. Our big topics are graph interpretation, two-dimensional vector addition, projectile motion, and relative velocity. Starting with graph interpretation. Graph interpretation is being able to describe the motion of an object using graphs. There are two kinds of graph interpretation. One is taking a graph and turning it into words. The other one is taking words and turning it into a graph. And you are expected to be able to do both. So I'm going to start with the simplest kind of graph, which is a position graph. This is a graph of position versus time. And here is the graph that we start with. Now this graph starts off as a flat line. That means that the object's position is not changing. The way I would describe that in words is the object is at rest for a time. So the object is at rest before it does anything. Before, and then here we have the position changing. The position is becoming more positive, which means our object is moving forward. And it is changing its position in a linear fashion, which means it's changing its position at a regular rate. A regular rate would be a constant speed. So I'm going to give myself. Now we have this next section here, which is the object not changing its position again. So the object then comes to a rest. It's at rest for a certain period of time, and then its position becomes more negative and goes down to 0. That means that this object is moving backwards. Before moving backwards. And this is a very steep line, which means that the speed is going to be fast. So it moves backwards quickly. We also need to take words and turn them into a graph. So we have an object moving forward, slows down to a stop before remaining at rest. For a time, and then moves backwards slowly. So I'm going to start with my axes, my position versus time. So I have to show that this object moves forward and slowly and slows to a stop. So our object needs to be moving forward, so it has a positive slope, which means that its position is becoming more positive over time. But it will eventually stop, which means it will eventually flatten out. So it will curve to a flat line where it is at rest for a time. Then it will move backwards slowly. So by that, there are multiple ways to interpret that phrase. The simplest interpretation, though, is that it moves backwards, so its position becomes more less positive or more negative, and it is shallow. Now, it could be a little bit more clear in the text, saying that it moves backwards slowly at a constant speed, in which case it takes away any questions I have on the whether or not this is linear at the end. The other thing we have to do with graphs is be able to convert between position, velocity, and acceleration. For this, we're going to look at our equations. V equals delta x over t. That's the definition of velocity. And acceleration is change in velocity over time. I can rewrite that first equation to give me change in position is equal to velocity times time. And the second equation can be rewritten as velocity equals acceleration times time. Those are important because every time we have a graph, you should always think about what would happen if I divided the y-axis by the x-axis, and then what would happen if I took the x-axis and multiplied it by the y-axis. So if I have position versus time and my graph looks like this, to get velocity versus time, I need to look at the change in position over time and how that is changing. I start off with a positive slope, and it becomes a zero slope. So my velocity starts off positive. I'm moving forwards, but eventually I come to a rest. My velocity becomes zero. Then going from velocity, I need to get my acceleration. My velocity starts off positive, ends up zero, but it is changing at a consistent rate. So my acceleration is consistently negative. Going down, we're looking at the slope, because slope is delta y over delta x. My y-axis divided by my x-axis. X divided by time gives me velocity. Velocity divided by time gives me acceleration. Going backwards, I have to look at what I get when I multiply my x and y together. Well, a times t gives me delta v. So if I look at this chunk right here, I can look at that and calculate the area. It's a negative area. That means that my velocity starts off somewhere, and then after that period of time has dropped down by a certain amount. Look at another chunk of time, I get another negative area. So over that next period of time, my velocity drops down by a certain amount. Next period of time, my velocity drops down by a certain amount. Those amounts are consistent because my acceleration is constant. I can also look at delta x being velocity times time. So I look at, let's just say this first chunk here. I look at that area. That's a positive area, which means that my position changes positively. Then I look at this area here. It's positive, but it's not as large as that first chunk. So from that time to the next time, my position changes positively again, but not as much. And then here, I have an even smaller change, so I have an even smaller change in position. The next part is 2D vector addition. So if I have an example, you walk 3 kilometers north, 4 kilometers east, 7 kilometers south, 3 kilometers west. What is your net displacement? So to figure this out, I'm going to give myself a visual representation of this. I'm going to give myself a starting point. And I'm going to draw this out. 3 kilometers north. Then 4 kilometers east. Then 7 kilometers south. Then 3 kilometers west. To my end point. Displacement is simply asking me to find from beginning to end, what did I do? What could I have done to do that same start and end point? I could have walked 4 kilometers south and 1 kilometer east. I can draw this as a triangle, and instead of walking 4 kilometers south and then 1 kilometer east, I could have just cut the corner. To find that hypotenuse, I would do the Pythagorean theorem, which gives me 4.12 kilometers. But I also need to describe what direction to go, since I'm not going straight south and I'm not going directly east. I have to say where to point myself. So I would need to describe this angle here. Inverse tangent of 1/4 is 14 degrees east of south. And that should do it for vector addition. It might not be that terribly important for kinematics, and in fact the whole kinematics unit's not super duper important, but the skills we learned here are used elsewhere. We always use vector addition when we do forces. We're always going to look at graph analysis in any unit. This brings us to projectiles. Projectiles are not super duper important for the exam, but it does teach us some of our skills. So our first equation for projectiles is the one we use most often. This equation, we never really talked about it, but you can actually derive this equation from a velocity versus time graph. So let's say that my velocity versus time graph looks like that. I need to find the position after I've traveled according to this velocity versus time graph. To find the position on a velocity time graph, you look at area. So I'm going to break this up into two shapes. I have a rectangle and a triangle. To calculate the area of the rectangle, this velocity here is my initial velocity, v0. This velocity there is my final velocity. To find the area of this rectangle, I just need to do v0 times t. Then I also need to find the area of this triangle. Triangle is 1/2 base, which is time, times the height, which I'm going to call change in velocity. Except earlier we said that change in velocity is area times time, or not area. Change in velocity is acceleration times time. So I can replace that delta v with an at, and that gives me 1/2 at squared. To find my change in position, I have to take this area plus that area. And that gives me this equation. The other equations we have are v squared equals v0 squared plus 2a delta x, and v equals v0 plus at. Let's give ourselves a scenario. An object is launched off a 100-meter tall cliff at 10 meters per second, 30 degrees above the horizontal. What is the range of the projectile? First thing I'm going to do is draw it out. I have my object that is launched at 10 meters per second, 30 degrees up. And it lands down here somewhere. I need to find that position, that delta x. Remember, in physics, the word range means change in horizontal position. Think driving range or shooting range. You're looking at how far you can hit the golf ball. And we know that this cliff is 100 meters tall. Anytime I have an angle, I need to break it up into components. 10 meters per second at 30 degrees above the horizontal. I need to figure out, okay, in 1 second, how far up has this ball gone? How far over has this ball gone? Using 10 sine 30, I get 5 meters per second up, and 10 cosine 30, I get 8.66 meters per second to the side. Now I'm going to break everything up into x and y components. In the x direction, I'm trying to find the horizontal position. I know that my horizontal speed is 8.66 meters per second. Horizontal speed is constant because our object will never accelerate in the horizontal direction, because the only force acting on a projectile is gravity, and that only acts downwards towards the center of the Earth. I don't know the time. Change in the y position is 100 meters down. The initial y velocity is 5 meters per second up. Final y velocity, we don't know. I do know that it will be down. Acceleration in the y direction is 9.8 meters per second down. And time, we don't know. trying to find delta x. Delta x equals v0 xt. I know v0x, but I don't know the time. So I need to find the time in order to find the delta x. To find the time, I'm going to look over at my y values. Delta y equals v0yt plus 1/2 ayt squared. Now I'm trying to solve for time. Time is here and time is there squared. This is going to be a quadratic. So I'm first going to put it in the format that I like for quadratics, which is 1/2 at squared plus v0yt minus delta y. Then I'm going to plug in my numbers. But when I plug in my numbers, I have to be careful about direction. Anytime you're plugging in numbers, you have to think about what direction is the vector pointing. I'm going to say that up is positive. So my acceleration is down. It will be negative 1/2 of 9.8, so negative 4.9 t squared, plus my v0y is up. It will be positive 5t. Then I have to subtract my delta y. I'm subtracting a downward value. I'm subtracting a negative value. Gives me a positive value. Now I need to find the time using the quadratic formula. I could also plot this equation in my graphing calculator and find the zero. I get a 0 at time equals 5.06 seconds, which I can then plug in over here to get a delta x of 25.6 meters. The last topic we have in kinematics was relative velocity. This is essentially measuring how fast something is moving according to a different reference frame. So how fast is an object moving compared to how another object is moving? So an example, a train is moving at 50 meters per second. Inside the train, a child throws a ball at 3 meters per second relative to the train. How fast is the ball moving relative to the ground? So here's my train, and it's moving at 50 meters per second. And inside of my train, I have my child who throws a ball at 3 meters per second. I'm trying to find the velocity of the ball relative to the ground. And that's going to be equal to the velocity of the train relative to the ground, plus the velocity of the ball relative to the train. You'll notice that my subscripts are always the object followed by the reference. Turns out that when I take the train relative to the ground and add it to the ball relative to the train, that first train and that second train cancel. So velocity of the ball relative to the ground equals 50 meters per second plus 3 meters per second, or 53 meters per second. Now this phrasing was a little inconsistent, or a little inaccurate, I should say, because I never said what direction the ball was being thrown. What if the child threw the ball towards the back of the train? Well, then the velocity of the ball relative to the ground would be 50 meters per second minus 3 meters per second, because I would have defined 50 as being positive. Therefore, if I throw it backwards, it would be negative 3 meters per second. Let's do a harder example. A car is driving at 20 meters per second relative to the ground. And a truck is driving in the same direction at 15 meters per second relative to the ground. How fast is the car moving relative to the truck? So if I'm sitting in the truck, how fast does the car appear to be moving to me? So I'm trying to find the velocity of the car relative to the truck. What I know is the velocity of the truck relative to the ground. And if I were to add those two together, the truck would cancel out and I would get the velocity of the car relative to the ground, which is something else that I know. I'm going to solve this for the velocity of the car relative to the truck. VCT equals VCG minus VTG. So velocity of the car relative to the truck equals 20 meters per second minus 15 meters per second, 15 meters per second, which gives me a value of 5 meters per second, which I could have done without doing all of the arithmetic. But I know that if I'm in the car, I'm going to observe this car passing me at 5 meters per second. How fast is the truck moving relative to the car? Now I'm in the car. I want to see how fast this truck is moving. I want the velocity of the truck relative to the car plus the velocity of the car relative to the ground. The two cars would cancel. I would get the velocity of the truck relative to the ground. Velocity of the truck relative to the car is then equal to velocity of truck ground minus velocity car ground. Velocity truck car equals 15 meters per second minus 20 meters per second equals negative 5 meters per second. If I'm in the car, it appears that this truck is moving backwards at 5 meters per second. In other words, I'm overtaking this truck. So that's a quick rundown of all of the topics in the AP Physics 1 Kinematics unit.